Today, we're going to talk about how you can perform a cyber risk assessment using exSILentia. We're going to go into a little bit of the methodology and why we do it the way we do it, and then I can show you how we do it in the tool itself. A little background, I should introduce myself. My name is Kate Hildenbrandt. I'm a product manager at exida. My focus is on feature road mapping and feature definition for exSILentia software. I am also doing training for the software, and I'm here to help you with any questions you might have on our exSILentia software. And for that reason, I have my email address right here at the bottom. If you have any questions on this webinar or on any topic at all, you can email me there and I can help. A little background on exida. We do have three main, we like to say, pillars of the company. One is that we provide enterprise tools like exSILentia, SIL Alarm, and SIL Stat. We also do lifecycle services. So one of our experts can help you to do this service. Anything in the functional safety lifecycle, alarm management, and cybersecurity lifecycle. We can have a consultant help you with that. We can help you with the tools. We can help you with the task free of the tools, whichever you prefer. We also certify both professionals and devices for functional safety and cybersecurity. And so all three of these work together very nicely to basically give you a full package of help for your safety needs, whether they be functional safety, alarm management, or cybersecurity. And hopefully we have an exida consultant close to you. We do have offices internationally, and here's a good map of that. I am located in our Sellersville office in the US, but hopefully you can get help from any of us internationally. So let's dive right in. We take a pragmatic approach to cybersecurity. What does that mean? Well, in general, a lot of corporations are realizing, as they should, that full management of risk at a facility or company-wide requires consideration of process hazards, as we know, but also consideration of cyber attacks. We hear a lot about data breaches, people hacking in and getting emails or data, personal information, that kind of thing. But what a lot of people aren't considering is that if a control system is compromised, that a cyber attack can actually cause the same process hazard that we're guarding against in functional safety. And so there are international standards for functional safety, cybersecurity that address these needs. How do we guard against these cyber threats? And we have one, as we know, IEC 61511 for functional safety. We have IEC 62443 for cybersecurity, and they're meant to analyze, design, and implement safeguards and countermeasures against these risks. But they're often carried out by separate parties with little interaction between them. So the methodology we're going to talk about today is basically going to try and open the lines of communication by leveraging best practices used during the functional safety lifecycle to also address your cybersecurity risks. So just for those of you, many of you are very familiar with the functional safety lifecycle, but we're going to take a look at it, kind of do a deep dive in the similarities between the life cycles. So this one is defined by IEC 61511. It's usually owned by engineering or process safety in a corporation. And obviously the scope includes analysis of the process for inherent risk, and then subsequent design, implementation, and maintenance of safeguards to protect against hazard scenarios. These safeguards can include alarms, they can include pressure relief devices, they can include safety instrumented functions, so on and so forth. There is a cybersecurity lifecycle. This is defined by IEC 62443. It's usually owned by operations technology and information technology within a corporation. And it has a similar scope. As you can see, there's an analysis phase, a design and implementation phase, and an operation and maintenance phase. And in this case, we're implementing countermeasures to protect against cyber attacks. These countermeasures can also include alarms with operator intervention. They would usually include things like physical security of the engineering station, checks on the network devices, things like that. And so we're going to take a deeper look into this. And like I said, the cyber attacks not only impact the business from a financial perspective, it doesn't only impact, corporate image, but it can also initiate those same process safety incidents. So it's really no longer adequate for plant operators, engineers, design support personnel to only really be focusing on process hazards and risk. Eventually, while you're running your plant, you're going to need an event response plan for your operator. He might know exactly what to do in case of a safety incident, but does he know what to do if there's a cyber threat happening? And part of the problem here is that you have differences in vocabulary and work processes that provide hurdles for effective communication between your operations technology and your engineering. But in reality, we should be aware of the overall picture, and we should have an event response plan that can address both safety and cyber hazards. So how do we do that? One thing we want to make clear one more time is basically that these cyber threats can affect the control system. They can affect your plant in the same physical way. So we like to have a few examples here. One, many people have heard of this. It's kind of the buzzword when you're talking about cybersecurity, is STUXNET. This was basically a cyber attack that was planned and executed between 2008 and 2010, and it targeted an Iranian uranium enrichment facility. The attackers overcame an air gap to the engineering stations, which means that they weren't connected to the internet, but they still accessed the stations by using USB drives to spread malware to the plant's PLCs. They basically infected over hundreds of thousands of computers at the facility and caused over 1/5 of Iran's centrifuges to physically degrade. So they basically ran them until they broke. This was obviously a huge hit to this nuclear plant to Iran. It cost a lot of money, a lot of downtime. And so this isn't just hacking for data, for email addresses, for credit card numbers. This is a very real process risk. Another such incident happened at a German steel mill in 2014. The steel mill is unnamed, but its control system was attacked through the corporate business network. This was achieved through targeted emails that appeared to come from a trusted source, and they either included an attachment or a link that downloaded malware to the corporate PCs. Through these PCs, the attackers accessed the control system and caused, again, massive damage to the plant equipment, including a blast furnace that could not be shut down. And one more good example is in 2015, the Ukraine's power grid was shut down, resulting in loss of power for hundreds and thousands of customers for several hours. In this case, the attackers accessed the corporate network, again, through an email campaign with malicious Word docs targeted at the IT and system admins. They essentially opened the Word document and it asked them if they would like to upgrade their macro, and that's how it basically open a backdoor into their system. Because of some of the countermeasures the Ukraine power grid already had, that wasn't enough to get into the control network. So they actually harvested remote login data and compromised the SCADA network through VPN login. And so once they were in, the attackers overwrote firmware on the critical devices. So they not only shut down power for hundreds and thousands of customers, but they also essentially left the devices that the operators were using fully compromised. So the operators had to control the breakers manually even after the power was back on. And so again, all of this is costing time and money to the corporation, and it's a big deal. Now, these are very specific cases where the cyber threat went straight to the control system. We have all heard about Sony hacks, credit card hacks, things like that, which might not have quite as high a consequence. And we have actually found that although there's a huge consequence to these very intentional cybersecurity incidents, the intentional ones are only 20% of all cybersecurity incidents. 80% are unintentional. What does that mean? So intentional usually have a very organized effort with a lot of money behind it, where people are doing a lot of reconnaissance. It can take years. They might be an insider, a hacker, or an outsider, a disgruntled employee. But the other 80% comes from basically stumbling and fumbling, things that aren't intentional at all. So just like the emails, even if they aren't targeted in a specific effort, you might open malware through an email, through a USB drive. You might have IT or a technician basically do something by accident that would allow malware into your system. And so most of it is the stumbling and fumbling, but we know that there's a huge consequence if it happens to be the intentional. And so we really need to implement enough countermeasures to protect against all of the above. This is such a real threat at this point that, of course, IEC 61511 now includes cyber requirements for the CIS. So it's something that can't be ignored. We're bridging that gap between, having two separate standards. The new version of 61511 emphasizes the need for a cyber risk assessment, including description of identified threats, the likelihood and potential consequences of a security event, determination of requirements for additional risk reduction, and the description of measures taken to reduce or remove the threats. And the emphasis, it definitely emphasizes the responsibility of the owner operating company of the facility to do the cyber risk assessment. And so it's something that engineering needs to take a good look at. Additionally, it includes requirements for design and operation phases also, which is basically physical security. You want to make sure that people aren't entering the plant. You want to do background checks to make sure that everybody there is trustworthy. You want to secure the engineering station, things like that. So those requirements are also now included in the new version of 61511. And so there's really a benefit here to opening the lines of communication by basically leveraging best practices from the functional safety lifecycle to use in the cyber assessment, so that not only are you doing an efficient assessment, but also essentially hopefully using some of the same language so that the different groups can get a bigger picture of the actual risk going on at the plant, not just the safety risk, but the cyber risks. And so you'd have a complete plant and enterprise view. And again, you might be saying, how do you integrate these life cycles? And this is what we're going to talk about next. So how do you do a cyber risk assessment using CyberPHAX? It's a lot like doing a process hazard analysis or a HAZOP. And here I'm showing basically the analysis part of both life cycles, and you can see the similarities. You're going to take a look at your process or your system for all risks. You're going to allocate protection layers, and you're going to write a safety requirement specification or a cyber safety requirement specification. So both of these involve breaking the system into smaller parts. For safety, the system starts with a piping and instrumentation diagram. For cyber, this starts with a zone and conduit diagram. You're going to break it into smaller pieces and analyze for inherent risk. Then you're going to define safeguards or countermeasures against that risk. Safeguards for safety, countermeasures for cyber. In both cases, it's important to note this includes alarms. And so if you do it this way, hopefully you should have a picture of all alarms that need to go into your alarm rationalization life cycle. And then in both cases, you're going to write a safety requirement specification. And this is going to communicate design criteria to the implementation team. For safety, this includes your design criteria in the form of target safety integrity level. For cyber, it includes design criteria in the form of target security level. And so for safety, this is just called the SRS. For cyber, it's the cyber SRS. So you can see how we're sort of using the framework of the functional safety lifecycle to also address cyber. Well, what does this actually look like? Well, this may be very familiar to you, but on the safety side, you do your process hazard analysis. For this, your process is divided into smaller parts called units or nodes. So you see here a piping and instrumentation diagram, and this is just a reactor, but you can say that everything you see here is the unit, and the node includes the reactor or the heat exchanger or the quench tank, and focus on each one to see where the inherent risk is. Any challenge to the process is called a deviation, and you need to document what causes the deviation and what is the consequence. So a popular one is high pressure. If there's high pressure in the reactor, what was the cause of that? Maybe it was the BPCS failed, and what's the consequence? In some cases, if it's the ultimate consequence, you could have a rupture in the reactor and an explosion. You need to document what is the risk, and the risk is based on the frequency of the cause and the severity of the consequence. Then you want to document all of the safeguards present, and that can be implemented. So these are going to include alarms with operator intervention, pressure relief devices, and safety instrumented functions. So that's how it works for safety. And this is an example of how that would look in a PHA worksheet. Again, here you're looking at high pressure, you have failure of the BPCS. You have a couple consequences. One is for safety and one is for business. Over pressure leading to excess temperature and runaway reaction could potentially rupture the vessel and people could get hurt. You also have loss of usable product, which means that you're losing money. Then you have your safeguards. So you have some high pressure alarms. You have an instrumented protective function and a rupture disk. And then obviously any recommendations are documented, and you might move on to analyze this in a LOPA. For cyber, it would look a lot the same. So this is where we get to the crux of it. For the cyber risk assessment, your system, which starts with your zone and conduit diagram, which is shown here, is divided into smaller parts called cyber zones and cyber nodes. Any challenge to the system is a threat vector, and this is basically the pathway that the threat would use to reach whatever their target is, if it's the control system, if it's the safety system, etc. Here you want to document what's the cause of the threat and what is the consequence. In this case, you would document what the risk is as well. The risk is based on the frequency of the threat and the severity of the consequence. Once the risk is determined, you can document countermeasures that are present that can be implemented against the risk. So in this case, that might include alarms with operator intervention. You might have firewalls, switches with access controls, and then of course things like physical security, locking down workstations, security, screening of employees, things like that. And to do this would look much the same. So this is your cyber risk assessment worksheet. This is an exSILentia CyberPHAX. And again, you're breaking down the system into cyber zones, cyber nodes. In this case, the cyber node is the BPCS controller, and then a threat vector. In this case, the threat vector is social engineering. So the threat is that an operator is blackmailed into sabotaging process control as a result of a national state level attack. What's the likelihood? It's medium. That's based on your risk configuration. And then you have some consequences. Again, you have a safety consequence and a business consequence. You have altered control settings for the reactor, resulting in excess pressure and temperature feed to the reactor, resulting in runaway reaction. Again, you could have a vessel rupture. In this case, the business consequence is also that there's loss of product and it's out of spec. And so you have a resulting risk for those, and then you implement countermeasures, just like you might implement the safeguards for safety. Here you can see there's a number of countermeasures, including firewall, inspection and verification of the controller code. Unnecessary controller ports are blocked. Access control list detailing who is permitted access to the engineering source file. security screening of all employees. All of these would basically be implemented to mitigate the risk of this specific threat. And so it works a lot the same. Of course, you would document recommendations, and you could, if the risk is high enough, move on to security level verification on this cyber event scenario. And so you can see how the cyber risk assessment is kind of simplified simply by leveraging the best practice of doing a HAZOP on your safety system. You can do the same on your network. And so that is what that would look like. It doesn't have to stop there. I mentioned SIL verification. We can do this using exSILentia's module CyberSL. And basically this is taking that one more step forward by using frequency-based targeting to determine your design criteria for your safeguards and your countermeasures. So for functional safety, we have a target SIL level that is determined through LOPA and SIL selection. The achieved SIL is determined through SIL verification. For cyber, it's a little different. Your target SL level is determined during your cyber risk assessment when you determine the risk. And then the achieved SL level, again, that's security level, is determined through SL verification, which is your frequency-based targeting. So you can see how this design phase is pretty similar. At this point, you're basically taking your safeguards and countermeasures and making sure that you've closed the gap between your target frequency and your actual frequency. So we've all seen this for functional safety. Hopefully, this is how you would go from your PHA to your LOPA. So essentially, your cause would become your initiating event, and your initiating event would have an attributed frequency per year. And then all of your safeguards are your IPLs. If they're not independent, you might not, you might delete them or you might not apply them. But you want to identify which protection layers or safeguards are independent and then what their probability of failure is. And together, the frequency and the probability of failure of each IPL give you your intermediate frequency. Up top, you can see that you want your actual frequency for this scenario to match your target frequency. In this case, we've attributed a risk reduction factor to the SIF to force them to equal each other. And so for this SIF, the target risk reduction factor is 100 and the target safety integrity level is SIL2. So that's LOPA and SIL selection in one. But basically, you're using your frequency-based targeting to make sure that you have enough layers of protection and that you're closing that gap between the target frequency and the actual frequency. And then, of course, you do SIL verification. This is our module Silver to determine if you have achieved that target SIL level in your SIF design. So that's how you would make sure your design is complete and that you've reached your design criteria. For cyber, when you do your SL verification, it's a lot like the LOPA. And so here you see, again, all of your cyber threats are shown here, and you assign a likelihood of attack per year again. It's a little different. In this case, some of the threats are not by accident. They're done on purpose. And so likelihood of attack might be sort of a low, medium, high instead of the frequencies we're used to in functional safety. And then each of your countermeasures are lined up. As long as they're independent, you can apply a credit for each countermeasure as it applies to the cyber threat. And together, your likelihood of attack and your credits will basically give you a mitigated likelihood. And you want your likelihood of success to basically match your target likelihood. If it doesn't, you're going to have a factor that will say that you basically need to implement more countermeasures. And so in that way, it works a lot like the LOPA, but what we're trying to do is quantify how much risk reduction you would need after accounting for each countermeasure. And so again, here we're leveraging our best practices from functional safety to make sure that our countermeasures are enough to mitigate this cyber risk. And so that is how you would do your SL verification. So all of this that I've shown you was done on in exSILentia. A lot of the screenshots you saw, we have CyberPHAX and CyberSL. They're all on the same exSILentia platform that our PHA, LOPA, SRS, and Silver tools are on. And so there are some things that you still benefit from if you're using, if you're doing your cyber risk assessment and security level verification. As always, there's knowledge capture. So as applies to cyber, you have a risk configuration that you're going to define. Maybe you have one corporate wide like you do for functional safety. Maybe it depends project to project, but you can go in and define your risk configuration for cyber just as you would. You can also go in and define for each cyber node what you think the threat vectors might be. And that's something I can show you in the demo. Obviously, there's a cyber risk assessment report and a CyberSL report that would come from the exSILentia tool. You also have data core features. So every single countermeasure that you would document is kept in a library. So you could use it for different, basically different scenarios. If a countermeasure applies to a couple different threats, you can just link it to those threats from the library. And if you have to update something about that countermeasure, it's going to update in all places. And so that's a nice way to keep organized. And again, the risk configuration I can show you. But the nice thing, this is on the exSILentia platform. So if you already happen to have exSILentia, you can add the cyber modules to it. When I pull it up, I'm going to show you just the cyber modules, but you can have them right next to your PHA, LOPA, so on and so forth. So if you're doing your HAZOPs and your cyber risk assessments in the same tool, you should be able to export all of your alarms into an alarm rationalization tool. So hopefully this keeps you a little more organized and you can have all of your safety information in one spot. All right, so I'm going to show you how this would work in exSILentia. I'm going to start with the dashboard. So here, if you're familiar with exSILentia, you might see something a little different. Instead of your usual modules, we have the CyberPHA and CyberSL modules. Now, like I said, and maybe I can show you at the end of the webinar, you can have all of these showing at the same time. If you're already an exSILentia user and you have both licenses plugged in, you would see PHA, LOPA, Silver, and so on. If you're just interested in cyber by itself, it would look like this. And so that's nice. When you go into your project configuration, you're going to see that you have some predefined cyber countermeasures. So if you're going through your cyber risk assessment and you're thinking, okay, well, what have we not thought of? What is it that we could implement here as a countermeasure? We do have some things, basically countermeasure types predefined. And so you have your firewalls, operator surveillance, patch management, things like that. And so we do have some predefined countermeasure types. For each cyber node, we have what we call threat vectors that are already defined. And so if your node is a firewall, some threat vectors might be social engineering, supply chain, communications, physical security, software, and hardware. And so just like the deviations in safety, once you have a node defined, this is going to walk you through and say, this is something that you should consider anytime you're dealing with a firewall. Just like you might have to consider high pressure, low pressure, mixing, flow, things like that when you're dealing with your process. So that's something that's already built into the tool as a default. And obviously you can add or subtract threat vectors, you could add or subtract node types and default countermeasures as needed. Next thing I want to show you is the risk configuration. So here you'll see the safety one, but we're focusing on cyber, so I'm going to move over here. Your risk configuration would allow you to consider business environment safety. You can add things here as you like using this plus button. You could put in corporate image, whatever else you might want to consider for your severity categories. And then we would define levels. So all of this is customizable by the user, but this would be basically our default severity configuration. You have your severity matrix, so you have levels here, level 1 through 4 for business, environmental, and safety. And this is all pretty qualitative, but it's basically saying for safety, level 1 would be interruption of authorized user access, resulting in negligible impact, For level 4, it's a comprehensive engineered attack using kill chain methodology, resulting in potential for multiple on-site fatalities. So that's kind of what we were talking about earlier with the 3 examples I gave you on cyber attacks. Basically a really planned, thought out, expensive cyber attack. And so you're putting in qualitative, you could put in quantitative values here. Again, this is customizable just like anything else in your risk configuration, but that's how you would set up your severity matrix. Then for likelihood, you basically just have low, medium, high in this case. You can expand upon this if you wanted to, but the idea is just to get an idea of what is the frequency of an attack like this when you're doing your cyber risk assessment. And then of course, this results in your risk matrix. This one is pretty simple compared to some of the functional safety ones. Obviously, once more, it's customizable. So you can put in, if you already have a corporate risk criteria for cyber, you can put that in here. So when you're doing your cyber risk assessment, you'd go to the CyberPHA tab. Here I already have a example problem, but here you would list your cybersecurity zone, your cyber node, and your threat vector. In this case, if we look at the BPCS controller, we have the social engineering threat vector, which is what we talked about. Basically, your operator could be blackmailed into sabotaging process control as a result of a nation state level attack. Here you would put in your likelihood. Is it low, medium, or high? And it's going to give you that criteria right here. So you can see, okay, let's say instead it's high. The consequence would essentially, here it's split up in a safety or business. So here you have a reactor resulting in runaway reaction, potential vessel rupture, which could cause fatality. In this case, it's saying it's a single fatality. Maybe only one person would be in the area. This is obviously a safety category, and we're saying the severity is that it requires security level 3. This is the resulting risk from the risk matrix. There's a business consequence, obviously. If there's a vessel rupture, you're going to lose product. It's going to be out of spec, and you're going to lose money because of that. And so you have the business category here. You have a severity based on business, and you have your resulting risk. Here again, you have the countermeasures. Each of these has an ID, which means that each is a library item. If I want to link something else from the library that I haven't used yet, this might not apply in this case, but I can link it straight from the library. You might notice that a couple of these match. So this code is validated with detailed signature before download is the same countermeasure for business. And so if I wanted to give this a tag, which may not make sense in this case, but you can see how it updates in both places. So that's one thing we do to help keep you organized, make sure that one countermeasure or the other is identified. In this case, that might not make sense, but if you're using a specific device, a firewall, something like that, that could be helpful, or an alarm. and then you'd have recommendations, just like you would in your PHA. And so you see how the cyber risk assessment can be pretty, the methodology can be pretty easy to walk through, just like the PHA is, to make sure that you're accounting for all of your risk when it comes to cyber threats. Now, at the end here, you can decide that I want to, if the risk is high enough, I want to continue to analyze this in security level verification. And that'll link all of this information to the CyberSL module so that you can continue to make sure that you have enough basically layers of protection when it comes to your countermeasures. So if we go to the CyberSL tab, you'll see this same scenario. Basically, you have a runaway reaction caused by the vessel rupture. In this case, this is caused by a cyber threat. And so you're seeing that same cyber threat here as basically an initiating event. So the operator was basically forced to sabotage the process, which resulted in a vessel rupture and loss of product. So here you can put in the likelihood of such an attack. We have a couple other cyber threats that would also cause the same, basically runaway reaction, possible vessel rupture, and loss of production. And so these are all on one sheet. Here we're just looking at the safety consequences, but you can look at the business and environmental consequences at the same time. That can get a bit busy, so I prefer just to look at one at a time. In this case, all of the countermeasures that we put in are now shown up top here, and you can put in a probability of countermeasure failure here, and that's basically going to show up here as it applies to each cyber threat, and your likelihood of attack combined with your probability of countermeasure failure is going to result in your likelihood, mitigated likelihood. So when all of these are combined, you have your likelihood of success, and you want that to match your target likelihood. In this case, it doesn't, so you have some remaining cyber risk, which you want to close the gap between. And so the idea here, we don't have any next step like SIL verification. We're going to, design an automated safety instrumented function for this, but you want to just make sure that you have enough countermeasures to mitigate the risk. And so you're doing that frequency-based targeting to make sure the gap is closed. And once it's closed, you've achieved your security level. So that's the way that would work. A lot of times we hear about cyber risk assessments and the importance of them, and they are very, very important. It's imperative that they're done. But when you're done, how do you know that you have actually accounted for all of the things you need to do to properly mitigate for that risk? So this is an attempt to do that in security level verification. And it's basically saying, okay, I know I have enough countermeasures to really guard against an attack like this. And so that is that. Go back to our slides. If you want to know more, you can always sign up for a free trial for any of our exSILentia tools on exSILentia.com. They will be on our cloud platform, and you can basically get a 2-week free trial. You can also follow us on exida LLC on Twitter for latest news and upcoming conferences, or to get a live demo. You can contact me at any time if you have any questions on what I just showed you. You can email me or call me at this number. And that is that. That is how you can perform a cyber risk assessment. Someone asked me, your examples seem to have financial impacts. Are there any that were hazardous? So the example that I showed had both. Let me go back to this slide. The example that I showed for cyber had both, and essentially it had a safety and business. And it was actually just like my process example where In this case, the operator was blackmailed into sabotaging the process. In the safety case, the BPCS failed, but the consequences were the same. Essentially, if you have an operator purposefully raising pressure, doing something to a reactor, you might have vessel rupture and fatalities due to that. This is a case where it's social engineering. There are other ways this can be done, as we saw with the STUXNET example, with the German steel mill example, that this can be done on the sly without blackmailing operators. But essentially, that would be your process risk, is that the vessel could rupture and you could cause a fatality. There is a business risk here as well, where you lose the product. But in this case, the example pretty much mirrors the safety example on purpose. So you can sort of see how the similar hazardous event could happen. Someone asked, why is the SIF not protecting against these risks? And that's a very good question. In some cases, I would say it's possible that a SIF could protect against the risk. It depends on how the attack basically happens. So if our initiating event in the safety case was basically that the BPCS failed, then you would have the safety instrumented system maybe act and mitigate that risk. However, if it's the safety instrumented system that's attacked by a cyber threat, then the SIF is basically compromised. And so in that case, you would need you would hope that before that happened, you would have some countermeasures in place to make sure that they couldn't get into the safety instrumented system. A couple people are asking basically, how do you quantify the effectiveness of the countermeasures like we do in functional safety? And I think with the CyberSL, you're essentially putting in that probability of failure like you would in the LOPA for functional safety. But we're so used to having SIL verification come next that people are saying, okay, well, how do we make sure? We don't have the kind of failure data for countermeasures or for cybersecurity that we have for functional safety, because that data has taken years and years to collect, and that process has basically been, I don't want to say perfected, but certainly optimized. In this case, we are taking the opportunity to basically do a semi-quantitative analysis of the countermeasures against a cyber threat. So you're basically doing the frequency-based targeting, you're putting in a probability of failure for those countermeasures, and you're closing the gap. And it's our best way to sort of try and ensure that you have enough countermeasures against the threat. So there is no next step like SIL verification in this case. All right. Okay, so if I've missed any questions, I can certainly document them. I'll answer them and I'll send them to the whole group. You'll also get a copy of the slides. And that's it. Thank you so much for joining us today, and take care.